Hi, and welcome to week 10. This week we're going to be developing the meaning of fractions. So in other words, it might be called Introduction to Rational Numbers. So because fractions are rational numbers, just so you know that rational numbers include the set of natural numbers, whole numbers, and integers are all part of the set of rational numbers, because rational numbers are any number that can be written as a fraction. So all of those can't be. All right. Look out week 10. Okay, so our objectives this week, we're going to explore the meaning of fractions, explore the meaning of the unit, compare and order fractions, find equivalent fractions, and explore the denseness of rational numbers to find fractions in between two given fractions. So the math practices we're really hitting on hard this week are making sense of problems and persevere in solving them, MP1. MP4, model with mathematics, and MP6, attend to precision. Before we get started, let's do a little flashback to last week. So confirm if the number in that list is prime or composite, and be sure to have evidence. So there's 8 of those, so pause the video, use your rules for divisibility and the theorem you developed from Eratosthenes' sieve, and determine if those are prime or composite. All right, did you get them all right? So only 1, 6, and 7 were prime because we checked all the prime numbers that are smaller than the square root of the number. The other ones are all composite, and we could check some of them using the divisibility rules, but some of them we don't have divisibility rules for, like 7 or 17. Okay, so you might have had to do different mathematics just using regular division to see if those numbers are prime or composite. All right, so here are some beliefs. This is from something called the Rational Number Project. Children learn best through active involvement with multiple concrete models. Physical aids are just one component in the acquisition of concepts. So we have verbal, pictorial, symbolic, and real-world representations that are also important. Children should have the opportunities to talk together and with their teacher about mathematical ideas. It's very different than maybe what you experienced growing up, but it is definitely part of the classroom today. Curriculum must focus on the development of conceptual knowledge prior to formal work with symbols and algorithms. So thinking about ideas before we start just memorizing rules or procedures is what that's saying. Fraction frustrations. So this may apply to you or it may not, but think about the challenges or frustrations you've experienced or ones you anticipate when you're teaching fractions to children. What makes fractions so difficult? All right, so we're going to investigate why fractions are so difficult for students. So how many numbers do you see here? Think about it. Is your answer 1? Is your answer 2? Is your answer more than 2? So how do you think about this fraction? We have students think about things differently. So for example, one of the ways to think about it is with the part-whole relationship. So as in 3 out of 5. The limitation to that model is, how do you interpret 5 to 3? Or how do you interpret 8 to 3/5? So the part-whole model is somewhat limiting. You could think about it as a ratio, as in there are 3 boys for every 5 girls. That implies a multiplicative or proportional relationship that may not be explicit for students. You could also see this as a division problem, as in 3 divided by 5. If this is your sole interpretation of this, it might be problematic and limiting. So we can think about it all of these different ways. Here are some fraction frustrations from the Rational Number Project. Children have difficulty internalizing that the symbol for a fraction represents a single entity. When asked if 2/3 was one number or 2 numbers, many children would say that the symbol represents 2 numbers. When students consider 2/3 as 2 numbers, then it makes sense to treat them like whole numbers. For example, when students add two fractions by adding the numerators and then adding the denominators, they are interpreting the symbols as four numbers, not two numbers. So many errors with fractions can be traced to the student's lack of mental images for the quantity the symbol represents. So what is a fraction? Suppose that this bar represents the whole or the unit. I'm going to refer to the unit throughout this, and that means the whole. The unit means the whole. Create a bar that is equivalent to 1/5 of this whole. Well, how would you do it? You would cut the bar into 5 equal pieces using 4 lines. Notice that. And then you would copy that. So you need one of those pieces. So a cut and copy activity is naturally what we would think of next after we're discussing this cut and copy idea. So try a few of these. Imagine a circle is cut into 4 equal copies. 3 1/4 copies are shaded. Write a fraction that tells how much is shaded in all, and draw a picture. The second one, instead of using a circle representation, it says imagine a rectangle cut into 5 equal copies. 4 1/5 copies are shaded. Write a fraction that tells how much is shaded in all, and draw a picture. The next one says draw a picture that illustrates the following. Then write the fraction number for each. A rectangle is cut into 7 equal-sized copies where 5 of the copies are shaded. So what does that look like, and what fraction is it? And then a rectangle is cut into 7 equal-sized copies where 0 of the copies are shaded. Draw a picture and say what fraction that looks like. When you have all of those finished, move on. All right. Here's the answers. The first one, I'm guessing you drew a nice circle split into 4 equal pieces and you shaded 3 of them, so that's 3/4. The second one, a rectangle with 4 out of the 5 shaded, that's 4/5. And a rectangle cut into 7 pieces where 5 of the copies are shaded is 5/7. And then the last one, 0 copies are shaded, which is 0/7. So here's another idea. So what is a fraction? Suppose that this bar represents a whole unit. Create a bar that's equivalent to 13/9. So the orange rectangle you see there is the whole. So what would you do? Think about what this means. All right, well, if the whole is that rectangle, first we split that rectangle into 9 equal pieces because the denominator is a 9. Then we have to add some pieces on the end. So 13/9 would be a whole unit plus 4 more. So if the whole bar is 1 unit and it represents the whole, if the denominator is 9, we're first going to cut up that rectangle into 9 equal pieces. Then if we want 13/9, we're going to have to add on 4 more copies of 1/9. So here's the whole, which is 9/9, and then we have to add 4 more copies. So we have 10/9, 11/9, 12/9, and 13/9. So describing a fraction 3/8, you can do 2 different things. You can describe it with partitioning and with iterating. So partitioning says 3/8 is 3 1/8, where 1/8 is the amount we get by cutting up the whole into 8 equal pieces, and taking one of those parts would be 1/8. So if we take 3 of those parts, then it's 3/8. Iterating means we think of it a little bit differently. We think of we have 3 copies of 1/8. So we first partition and then we iterate. Okay? So you try it using 5/6 with partitioning first and then iterating. So with partitioning, 5/6 is 5 1/6, where 1/6 is the amount we get by taking a whole, cutting it into 6 equal parts, and then taking 5 of those parts. And iterating says 5/6 is the amount when we have 5 copies of 1/6. That copies of idea, remember we started that in multiplication of whole numbers. That's going to really continue through here, and you're going to have to get more comfortable with using that wording. So here's some Common Core standards. So in 3rd grade, they develop an understanding of fractions as numbers. They understand a fraction 1/b as the quantity formed by one part when a whole is partitioned into b equal parts. Understand a fraction a/b as the quantity formed by a parts of size b, or a copies of size 1/b. Understand a fraction as a number on a number line. You probably haven't done that much, but you need to start. And represent fractions on number line diagrams, explain equivalence of fractions in special cases, and compare fractions by reasoning about their size. So here's an interesting idea. Take out a blank piece of paper. Imagine that the sheet is 4/5 of some larger sheet. Can you fold your sheet of paper in such a way that you can easily show me what 3/5 of the larger sheet looks like? Try that. All right, I don't know how well you can see this, but it said take out a blank piece of paper, imagine that the sheet is 4/5 of some larger sheet. Can you fold your sheet of paper in such a way that you can easily show me what 3/5 of the larger sheet looks like? So here's my piece of paper, and I split it into 4 pieces because it was 4 copies of 1/5. If I just fold one piece behind there, I see 3/5. So this is 3/5 of the larger sheet. I didn't show the whole or the unit. I'm only showing the part they asked me to. All right. Fractions as numbers on a number line. Since we've said that fractions are numbers, they have to have a place on the number line. How would you place 2/3 and 4/3 on a number line? Pause the video here. Draw a number line. It's probably nice to have 0 and 1 labeled, or 0 all the way to 2 labeled, and then see if you can accurately mark where 2/3 and 4/3 are. Okay, here is 2/3 and 4/3 on a number line. You can see that I've broken the number line up into thirds. We could label all these tick marks. This would be 1/3, 2/3, 3/3, then 4/3, 5/3, and eventually 6/3, which is equivalent to 2. You have an activity where you have to put numbers on a number line a little bit creatively on your Google Jamboard assignment this week. Here's an interesting quote just to remind us. The most difficult lesson in life to learn is which paths to take and which to avoid. But in this course, the most difficult lesson in mathematics to learn is which paths to take and which paths to avoid. You might appreciate that after some of your problem solving in this class. All right, the next thing we're going to talk about is your home activity, exploring the unit. So you have an assignment on Canvas where you explore the unit. You're going to have a PowerPoint open that you're following along with, and then you're going to have a PowerPoint open where you're entering the answers. Okay? It's actually not a PowerPoint, it's actually Google Slides. So make sure you follow those directions carefully. You're going to download your final answers as a PDF from that Google Slides, and then you're going to upload them to that assignment. That assignment can take some time, so don't wait till the last minute. It's worth a lot of points. Okay, you have a video assignment on Canvas about fraction representations and why students struggle with fractions. You're going to make your own foldable. Here's an example of one where we show fractions with a number line, a circle, and fraction bars. Your foldable doesn't have to look exactly like this, but I wanted to give you an example. And you'll upload that foldable to Canvas. Okay, let's talk about comparing fractions. You're having some friends over and you order 2 large pizzas from Papa Joe's Pizza. One pizza has pepperoni and one has sausage. Both pizzas are the same size, but the pepperoni pizza is cut into 8 equal slices and the sausage pizza is cut into 10 equal slices. Why? I don't know. So your friend Josh ate 3 of the pepperoni slices and your friend Chase ate 3 of the sausage slices. Did they eat the same amount of pizza? If not, which friend ate more pizza? Think about that and make a decision. So the fraction 3/8 is the same as 3 copies of 1/8. The fraction 3/10 is the same as 3 copies of 1/10. Now, you may or may not be able to compare those unit fractions. These fractions had a common numerator, so we're comparing the denominators. Since the fraction 1/8 is greater than the fraction 1/10, we can say that 3/8 is greater than 3/10. So the size of the pieces are what's different here. They both ate 3 pieces, but the pieces weren't the same size. The ones that were 3/8 were larger than 3/10. This is called comparing fractions with the same numerator. If you have that Math Power Book, these images are straight from that Math Power Book, so please refer to that and go through some more examples. So what I like about this is it also shows you things on a number line. So in this case, it's comparing 3/8 to 3/4. Again, the number of copies are the same, right? The number of pieces are the same. They both have 3 pieces, but the whole was cut into different size pieces, right? Because on 3/8, the whole was cut into 8 pieces. On 3/4, the whole was cut into 4 pieces. So you can see that the 4th size pieces are larger than the 8th size pieces. Pizza scenario number 2. You're having friends over, you order 2 large pizzas from Papa Joe's Pizza. One pizza is pepperoni and one has sausage. Both pizzas are the same size, but now they're both cut into 8 slices. Your friend Josh eats 4 of the pepperoni slices, and your friend Chase eats 5 of the sausage slices. Did they eat the same amount of pizza? If not, which friend ate more pizza? Make sure you can defend your answer. Now, in this case, our numerators are different, but our denominators are the same. This you're probably much more familiar with, but let's look at it with copies of statements. So the fraction 4/8 is the same as 4 copies of 1/8, or the fraction 5/8 is the same as 5 copies of 1/8. Since 5 is larger than the number 4, we can say that 5/8 is greater than 4/8, because now the pieces are the same size. And we just have more pieces because our numerator indicates the number of copies or pieces. So comparing fractions with the same denominator. Again, we can just tell who has more pieces because now the pieces are the same size. Sometimes we have a different scenario. Which fraction is larger here? You have friends coming over, you order 2 pizzas from Papa Joe's Pizza. One pizza has pepperoni, one has sausage, but both pizzas are the same size. Your friend Josh ate 3/5 of the pepperoni pizza, and your friend Chase ate 5/8 of the pepperoni pizza. Of the sausage pizza. Did they eat the same amount of pizza? If not, which friend ate more pizza? Work with yourself and figure out if you can figure out the answer to this problem. So you could use pictures to do this. You could shade 3/5 of the pizza here. You could shade 5/8 of the pizza here. If you put these images together, you can tell. Now, we can't use the first rule where we had the same numerator to compare these, and we can't use the second rule where we use the same denominator to compare these. But we can make a common denominator. In this case, it would be 40, and we could compare our numerators, which you're much more familiar with this. There is a third way to compare fractions, and that's using benchmark fractions that we'll talk about in a little bit. Sometimes a benchmark fraction is very helpful. Benchmark fractions are fractions like 1/2, sometimes 1/4 or 3/4, but 1/2 is the most common benchmark fraction. You can also use 1 as a benchmark, it's just not a fraction. So sometimes you can tell that one fraction is less than 1/2 and the other fraction is more than 1/2, and that helps you determine which one is larger. We could use fraction equivalence. That's how we get a common denominator. So any fraction is equal to infinitely many other fractions. And there's an example. If I asked you to tell me a fraction that's equivalent to 1/2, you could give me lots of different fractions. And then we could show it in a picture. We could also go back to a number line. Here's a number line. And we have this strip diagram up there, and we might be able to see how we have 3/4, 6/8, 9/12, and 12/16. Speaking of number lines, why don't you try to pause this video and plot these numbers on a number line. You'll notice it goes 1/4, -2/3, 1, 0, 6/5, 4/3, and -1. So how far in the positive and negative direction would your number line need to go? Try that, pause the video, and then play it again. If you're stuck, or one strategy you might have used, because these all have different denominators, you could use a separate number line for each one and then put them on the final number line altogether. That's how I did this problem. So if you look at my first number line, I split it into fourths and I plotted 1/4, and that's in blue. On my second number line, I split it into thirds and I plotted -2/3 and +4/3 in red on that case. The next number line I split into fifths. I needed to show 6/5. And I didn't ever model the 0, 1, and -1 until the last number line. So I put them all on a number line. Notice I don't have all my tick marks labeled. Normally I would say you have to label all your tick marks. But in this case, since these denominators are so different, it would be very time consuming to put in those tick marks that are necessary to have all the same ones. But using these three number lines, I can tell, notice I lined them up exactly. 1/4 is here, 2/3 is here, sorry, that's -2/3. 6/5 is to the left of 4/3, and I can tell that right here. So I'm able to put, and I also numbered -1, 1, I should have put a dot right there at 0 on my number line. So that's one strategy that might help you. We talked a little bit about common denominators already, and you can think about putting them in equal sized pieces. So if you have 1/2 and you have 2/3, notice these real faint lines right here. If we make them have the same size pieces, we can tell that 1/2 is 3/6 and 2/3 is 4/6. So then it's easier to compare those. Ordering fractions is more complex than ordering whole numbers. Comparing 1/4 and 1/6 conflicts with children's whole number ideas. 6 is greater than 4, but 1/4 is greater than 1/6. So you see where students might get confused. With fractions, more can mean less. The more equal parts you partition a unit into, the smaller each part becomes. In contrast, 3/5 is greater than 2/5 because 3 of the same size parts are greater than 2 of the same size parts. In this case, more implies more. Being able to order fractions plays an important part in estimating fraction addition and subtraction, which is what we're going to get to next week. Ideally, when a student adds, for example, 1/4 plus 1/3, she should be able to reason from her mental picture of the symbols that, first of all, the answer is greater than 1/2, but less than 1, and 2/7 is not a reasonable answer because it's less than 1/2. So that's a nice way for them to know, oh, there's no way I can just add the numerators and add the denominators. We'll revisit this next week. How about comparing fractions? This just goes over what we were talking about before. You can use common denominators, common numerators, benchmark fractions. This, converting to decimals, is your last strategy, because if you think in terms of elementary students, they don't have access to a calculator. So that last strategy of convert to decimals is not going to be most effective for them because most of them long division would be time consuming. So any of these three would be helpful. Benchmark fractions, this is what we were talking about earlier. They're easy to identify. One of the biggest benchmark fractions is 1/2, and you can compare with that. You have an ordering fractions activity on Canvas that you should make sure you don't forget to do, and it is a little bit time consuming. If you're struggling with number lines, GeoGebra, which is a free program for you, can help you with some number lines. If you use this link, you can visualize fractions using number lines and circles to better understand how to compare fractions. So for example, 7/15, and you can change these sliders around. You can move these sliders. 4/15, 10/15, and so on, and it moves it on the number line. And you can do the same with the other fractions, so you can compare. Okay, so these have same numerator, different, and then they can show the comparison, which is really nice. So that's just another option for you. So what did we learn from this activity? So what reasoning would help you explain that 3/7 is smaller than 4/7? What strategy are you using? Common numerators, common denominators, a benchmark fraction? How about the second one? What reasoning helped you determine that 7/36 is less than 7/34? Since they have common numerators, you do not have to get a common denominator. You can just compare the size of the pieces. And then how about that last one? How do you know that 3/5 is greater than 5/14? It doesn't have a common numerator. It doesn't have a common denominator, but you could use a benchmark fraction of 1/2. I know that 3/5 is more than 1/2 because half of 5 is 2.5. And I know that 5/14 is less than half because half of 14 is 7. So I can compare those and explain my reasoning. You have an activity on Canvas where you write the fraction rules. Be sure to read directions. It says write a general rule for comparing fractions with equal numerators for the first one and equal denominators for the second one. Try to use a copies of statement so you're used to it. It also says provide a specific example and use drawings to illustrate the rule. Okay, so be sure you have all three of those things: a rule, an example, and a drawing. Now we'll get to some fraction challenges. Find two fractions between 1/3 and 2/3. And then it says plot all four numbers on a number line. Some students are like, wait a minute, there's no space there between 1/3 and 2/3. How would I do it? Well, this goes back to the denseness of rational numbers. We can't keep cutting our whole into more and more pieces so we can see space between there. You can do that mathematically, or you can do it visually, or both. I would like you to try it visually first, and then if you have to fall back on your mathematical abilities, that's fine too. The second question is a little bit harder. Find two fractions between 1/3 and 1/4 and plot all those on a number line. I'm going to give you a little hint to get started. So if you're trying to find two fractions between 1/3 and 2/3, first plot 1/3 and 2/3 on the number line. Then you will be able to see, oh, how can I break this up further? The second one, find two fractions between 1/3 and 1/4. This might be a little harder to see that space. You might even want to make this part of the number line on the left 1/4 and the one on the right 1/3, because then you could see space between them, and 1/4 is smaller than 1/3. This one you might have to get a common denominator to really understand what's happening here. Pause this video, finish those, and then move on. All right, here's a couple answers. There's a lot of acceptable answers. So two fractions between 1/3 and 2/3 is 5/12, 1/2, which would be 6/12, and 7/12. How I did that was I found 1/3 and 2/3. Then I split each one of those thirds in half, which gave me 1/6. Then I've split each one of those in half, which now my number line was in 12ths. So I labeled all of those 1/12. This was already labeled 1/6, which is the same as 2/12. Then 3/12. 4/12 is the same as 1/3. 5/12. 3/6 is the same as 1/2 or 6/12. Then 7/12. Then 2/3 is the same as 8/12. 9/12. I had this 5/6, which is still 10/12, and then 11/12. So now I can clearly see these fractions between there. The other one was a little more challenging, between 1/4 and 1/3. The first thing I did was split it in half, but I was like, how do I find the middle between 1/4 and 1/3? The first thing I did was get a common denominator. So I made it 3/12 and 4/12. And then I was like, oh, I still can't see any space there. So then I doubled it again, and I made it 6/24 and 8/24. Now I could see the middle between 6/24 and 8/24. It's 7/24. But then I was like, oh, how am I going to find the middle of those pieces now? So I split it again, and I said now I have 14/48, which would mean this one to the left is 13/48, this one to the right is 15/48, and then I could find those fractions in between. I could do it mathematically, but I wanted you to be able to plot it on a number line. So make sure you review that. Some students use very non-traditional ways to get the answer, and I'll show you that on the next slide. This student was asked to get a fraction between 7/11 and 7/12. And they said, okay, well, I know that these three fractions would be in between 7/11 and 7/12. So 7/11 and 1/5, 7/11 and 1/4, and 7/11 and 1/2. I would have never thought of that. Look at their mathematical procedure they then followed. So they left their numerators the same. They changed their denominator into an improper fraction. So they multiplied 5 times 11 plus 1 and got 56/5. Then they followed their procedure that they must already know for long division of division of fractions, and they simplified all of these. So their three fractions in between 7/11 and 7/12 were 14/23, 28/45, and 35/56. If you like a challenge, try that strategy. So fraction ideas, this is where we're moving towards. We use fractions because we see them in everyday life. So here's an application of fractions. Suppose that 6,070 is 5/7 of the price of the car. What's the price of the car? So think about this visualization that we've been doing with what does 5/7 look like? And so that 6,070 would be split between how many pieces? So think about what it would take for you to solve the problem. Now, if a student was to have understanding of mathematics, a profound understanding of mathematics, what would they need? Here's a solution on the next slide. This student said, oh, I'm going to split this into 7 pieces because my denominator was 7. But I know the 6,070 was only 5 of those pieces. So if I divide it by 5, that's going to tell me the size of each piece. So 6,070 divided by 5 represents 1/7 of the price of the car. If I copy 6,070 divided by 5 7 times, I find 7/7 of the price of the car, which would be my answer. I hope you found this week a little bit different because now we've moved into fractions and our ideas are a little bit different. I know some of you are proficient in fractions with your algorithms. Right now I want you to focus on the meaning of fractions, not the algorithms of fractions. All right, Good luck on your homework. That's the end of week 10. You have a lot of assignments this week, so don't wait to get started. Let me know if you need anything.